Well, we're going to explore some exciting challenges to astronomy. That's why I'm calling this Beyond Newton. We're going to discover that Sir Isaac Newton has had a profound influence on the astronomers, but they haven't looked beyond that in some sense. Now, this is the fourth of a series of three. That may sound funny, but about 16 years ago, we published a series of studies. One was called Beyond Time and Space, which we've just republished afresh. And it primarily dealt with the impact of Einstein's theory of relativity and our understanding of the Bible. We talked about the nature of time, the nature of space and hyperspaces, and the challenge of nonlinearities all around us. That was all taken up in that first publication, which we've recently republished and freshened up. A second member of the trilogy was Beyond Coincidence, evidence of deliberate design in the universe and in the Word of God. We talked about the anthropic principle, the apparent reality that the universe seems to be designed for man. And we also talked about hidden messages in plain sight. All that was in Beyond Coincidence. And we explored statistically, how sure can we be of these things? We glibly talk about the Bible being the Word of God. That sounds great. How sure can we be? And we dealt with that in empirical terms. And then the third of the trilogy was Beyond Perception. And this was an exploration of the nature of matter, the subatomic world, and how it even it appears that we may be in a holographic universe. We're going to discover, and also we explored dimensions beyond our own. So one of the things you should recognize that we're going to borrow on some parts of all of these for this fourth member that we're going to add. We had this trilogy, we're adding a fourth member to it, and there will be a little bit of duplication here. You'll see why. I'm calling this fourth addition to our traditional trilogy Beyond Newton. And we're going to challenge here the myths of astronomy. And it really shocked me to realize how much of what we think we know about astronomy ain't necessarily so. And so I'm also going to throw in a little addenda in here I'm going to call Epistemology 101. What do I mean by that? I'll explain when we get there. We'll talk a little bit about the scientific myths of the past and of the present. And we'll talk about the milestones of influence that have occurred to bring us to this point. And we're going to show you a celestial model called the Burnham model. It's a standard model, but the implications of it may surprise you. And so we're going to lead then, of course, to the discovery, at least for us, of what some people call the plasma universe. So let's take this little preamble I'm going to call Epistemology 101. Epistemology is just a fancy word for the study of knowledge, its origin, its scope, and its limits of knowledge itself. And if you take this in college, it's a waste of time because it's administered by the Department of Philosophy, and it just becomes a study of the use of words through history. They don't talk about resources or tools as you would expect them to. And I love to start with this little quote from Look Through the Looking Glass. Alice says, "One can't believe impossible things," she laughed. "I dare say you haven't had much practice," said the Queen. "When I was your age, I always did it for a half an hour a day. Why, sometimes I believed as many as 6 impossible things before breakfast." And of course, that's Lewis Carroll with his tongue in his cheek, pointing out something that we all are guilty of, believing impossible things. So I want to talk a little bit about the myths of the past. We believe that there were many ancient cultures that believed the earth was flat. And they should know better because your Bible tells you several places, Isaiah 40:22, that the earth is a circle, a sphere. And another thing that came along in the 17th century was the idea of phlogiston, which is a material that caused things to burn. That was the way they thought things burned, because they had this peculiar material in it. And obviously we know they learned that it's actually oxidation, and the whole concept of burning was in error for a long, long time. It's a classic example. We all probably know about the Ptolemaic cosmology. The idea in the days of Ptolemy, they thought that Earth was the center of the universe, that the sun rose in the morning, set in the side. They actually had what's called a geocentric concept here. And that, of course, was replaced by what we call the Copernican cosmology, where the sun is the center of our solar system. Not of the whole universe, but of our solar system. Ptolemy, of course, in Alexandria, he is going to go down in history as opposing two fundamental truths in science. He, of course, was wrong about having a Earth-centered solar system. We know we have a sun-centered solar system. He also argued it was impossible to have four dimensions, interestingly enough. He proved that a fourth dimension was impossible because he couldn't visualize a fourth thing perpendicular to the other three. You think of one line, the idea of orthogonal or perpendicular, he said it was impossible to have four, and of course he's wrong, and he's going to go down in history as being wrong on both of his main points here. Higher geometry, in fact, is the key to understanding other conceptions of our universe. We covered that in one of our previous sessions. But another myth for a long time, they looked for ether. Ether was the medium by which light can travel through the universe. How can light travel from here to the moon? Must be something in there for it to travel in. They call that ether, look for it, and so forth. But the Michelson-Morley experiment back in 1887, which incidentally occurred on the Naval Academy grounds, by the way, proved that ether didn't exist. They tried to measure it didn't exist, so that punctured a common myth of the time. The velocity of light is another one, and it was interesting that it was under Descartes and so forth, they thought light was, the speed of it was infinite, or putting another word, light was instantaneous. And but an astronomer by the name of Römer, Olaf Römer, found a way to measure the speed of light by watching the eclipse of a moon on Saturn, and so he measured it, the speed of light, that it was very fast but finite. And it wasn't for 50 years later that Bradley, an Englishman, did the same thing, and they finally accepted that light had a specific speed. The interesting thing here, aside from the physics of light, is to realize even the physicists, it took them 50 years to swallow the meaning of empirical data. That we can constantly create theories that are not quite correct and cling to them in the face of experimental data to the contrary. When you find something that doesn't agree with your theory, you find an excuse to throw it out. No, we should be listening to it. And we always thought that light was a constant. Satterfield-Norman has discovered it's not a constant. We'll talk a little bit more about that in our next session. This velocity of light, see, in the 17th century, Kepler and Descartes, they thought it was instantaneous. But it was Olaf Römer in 1677 that looking at the eclipses of Jupiter with its two moons yielding a finite speed of light. And it was 1729 that Bradley confirmed that, but it took 50 years for acceptance. And so, well, let's talk about the myths of today. These, we look back at the laugh and we smile at the people, they had these wrong answers. Today we have evolution, which is provably not true. And that when I say evolution here, what I really mean is biogenesis, but everybody calls it evolution. Michael Denton, Philip Johnson, Michael Behe, these authors have written books in recent years that destroy, that demonstrate that evolution no longer is a viable explanation for what we know about the universe. And yet, it's still taught in schools. Our whole society presume it's a myth that everybody accepts. It's contrary to fact. The velocity of light is a basic constant. And of course, Satterfield-Norman, that many people still believe that, by the way. Many physicists do. But it's been statistically confirmed that it's been slowing down. We're going to talk a little bit more about that in the next session. Well, I want to talk about another one that's more at home to some of the things we're going to talk about here today, and that's the thing called the nebular hypothesis. Where did the planets come from? And Immanuel Kant and Laplace embraced this idea, and we want to talk a little bit about that. And it goes something like this. And Immanuel Kant wrote in his General History of Nature and the Theory of Heavens, he says, some 4 billion years ago, the sun had ejected a tail or a filament of material that cooled and collected and thus formed the planets. So it goes. Now, these ideas are still taught in college courses today. Understand that. 21 years before Kant said that, a guy by the name of Emanuel Swedenborg, that's where the idea came from, that he wrote it in Latin, but it became, he was a mining engineer with a lot of interests, and he claimed to have psychic powers. And he claimed that he learned this from seances with men on Jupiter, Saturn, and other places. In other words, he was a mystic in the negative sense. But he came up with this idea. When Swedenborg was 24 years old, he had an opportunity to meet Edmund Halley of Cambridge, who was famous for the comet and all of that. And so he had some astronomy background, and he came up with this idea that's where the planets came from. And Kant picked it up and published and sanctified it by giving his credibility to it without check, and then so did Laplace, and Laplace should have known better. Pierre Laplace he lent his endorsement to Kant's theory without checking the math, and he was capable of doing that but failed to do so. So then this nebular hypothesis gained widespread respectability despite the fact that it includes very serious mathematical errors. And subsequent writers have continued to develop variations of this view, even though increasing difficulties make it highly unlikely, and yet it's still taught today. The sun contains, it turns out, about 99.8, say almost all of the mass of the solar system. We're talking about the planets, the sun and the planets. Almost 100% of the mass is of the sun. It's gigantic in comparison. Yet the sun contains only less than 2% of the angular momentum. That's a strange thing. The angular momentum is all concentrated in the planets. The 9 planets contain 98% of the angular momentum. There's no way to explain how that happened. It's there. You can measure it. It's real. What causes it to be, it turns out there's no way to explain how that happened. All this was known in the time of Laplace 100 years ago, but he didn't think it through. That's why the nebular hypothesis doesn't make sense. There's no plausible explanation that would support a solar origin of the planets. But it gets worse. James Jeans, that's in the from 1877 on, pointed out that the outer planets are larger than the inner ones. Jupiter is almost 6,000 times as massive as Mercury. It's almost 3,000 times as massive as Mars. And so that's hard to explain. It goes against the concept here. And so this is a difficulty for all current theories. I'm going to show you before we're through, there's some theories that explain this, but we'll move on. Some other enigmas. There are 3 pairs of rapid spinning rates among our planets, each within 3% of others. In other words, the planets there's in pairs in which they're almost the same numbers. And so the Earth and Mars, Jupiter and Saturn, and Neptune and Uranus, they're all within 3% of each other in terms of the way they spin. Earth and Mars have virtually the identical spin axis, about 23.5 degrees. That's what gives us our seasons, spring, summer, and so forth. Why? Why do these planets, why are they in pairs? Nobody knows. From angular momentum and orbital calculation, it would seem that 3 pairs of these planets may have been brought here from elsewhere. They're somehow came out of some phenomenon yet undisturbed. Why does Mars have 93% of its craters on one hemisphere and only 7% on the other? It would appear that over 80% occurred within a single half hour. Why? See? Well, the planet Mars, of course, is a mystery anyway. It's the 4th major planet from the sun. It's named after the Roman god of war, Mars. We still use that term, martial arts, and so forth. Most of the early civilizations were terrified of that planet. Why? It was the Baal of the Old Testament, incidentally. Why? Well, first, what we discover when you get into this, you'll discover that scientists fall into 2 categories. Most of them are what we'd call uniformitarians. They mean they cling to the idea that things have remained essentially unchanged over billions of years. That's one philosophy. There are others that are called catastrophists. They believe that the universe has been subjected to a series of catastrophic events. That's what gives you all these. Look at the moon through a pair of binoculars. It's been beat up. And as we send probes to the other planets, we see the same thing. There's craters. The solar system is it's a rough neighborhood. And the fiat creationists, by the way, those of us that believe the Bible, would be in the second category. That would be categorized as a catastrophe. God intervened to make these things happen. The uniformity delusions are, view any surface in the solar system, there's craters and disruptive influences. Under a constant rain of interplanetary debris, the Earth itself still collects about 100 tons of extraterrestrial material per day. Many people don't realize that. There are over 100 craters on the Earth that by erosion and so forth, they're not as conspicuous. There are asteroid impacts all through history. Tunguska in central Siberia in June 30 of 1908 is a very famous one. It destroyed over 2,000 square miles of forest, or kilometers of forest. It was so remote that it wasn't explored for 17 years later. It's really a remote place. The damage there is equivalent in megaton, in nuclear terms, of like a 15 megaton equivalent. There's a meteor crater near Winslow, Arizona. It's a mile across, often visited. And they've discovered a big one on the Yucatan Peninsula at about 6 miles in diameter, 100 megaton equivalent. Apparently, it's about every 300 years we have one hit the Earth, and there's 1 in 3 of these are on land. The other 2 are, of course, in the ocean, so you don't see signs of it. Well, see, the ancients were sensitive to this, apparently. There was a meteorite that created the whole, that ends up creating the Kaaba in Mecca that they still worship, a meteorite stone that's in there. 2,000 years before Muhammad. That wasn't invented, that's something Islam adopted. It was there thousands of years before. The word Cairo, the city of Cairo, was named, that's Arabic for the planet Mars. Why? What's that got to do with pyramids and all of that? And of course, that's the site of the Great Pyramid and so on. Athens, we all speak of the Areopagus in Acts 17. Ares is the name in Greek for Mars. It's pictured as a source of judgment, really. Yeah, Mars Hill, that's why they call it Mars Hill, and the Areopagus in Greek. And Dionysus was a member of that sect. Well, in the Bible, of course, we encounter a strange event called the Battle of Beth Horon in Joshua chapter 10. The kings there confederate against Adonai-Zedek, the king of Jerusalem. He's sort of a foreshadowing of what we call today the Antichrist. He's defeated with stones of fire from heaven. And the sun was commanded to stand still, be silent, to give Joshua more time to complete the route. And the sun and the moon were extended apparently for the equivalence of a whole day. And kings hide in caves and are dealt with, and that completes the whole southern strategy of Joshua's thing, and the rest of the book of Joshua is just a cleanup after that. Well, what is this business of Joshua asking the sun to stand still? Most of us think, well, gee, that would mean the earth would have to stop spinning. No, it turns out all you'd have to do is change the precession a little bit. You would accomplish the same thing. But it's interesting, we discover that all ancient calendars were based on 360-day years. And typically 12 30-day months making a year. But then they change. In 701 BC, all these ancient calendars have adjustments made to them. We discover that Mars was worshipped by the ancient cultures, and out of all of this background, there is a hypothesis that is hard to disprove, that Mars made near pass-bys to the Earth. I'll come to that in a minute. But the idea is that Earth and Mars originally were on resonant orbits. Resonance, the orbits act just like tuning forks. If you have a tuning fork that you hit and there's one of the same frequency across the room, it'll resonate to it. Orbits are the same way. Orbits will have a tendency to get in step with either the primary or the harmonic of its rotation. Well, the Earth and Mars apparently are believed to be originally on resonant orbits. I'll show you a diagram here in a minute. And they had near pass-bys every 108 years. And it turns out by modeling this, it would account for catastrophic events on a number, in fact 7 of them, throughout recorded history. And these energy transfers all apparently stabilized in 701 BC, which caused the calendars to be redone. And so let's take a look at this. You have the Earth. We know that the Earth is at the foci of an ellipse, and like all of them are. And it's not necessarily a circular, it's an oval, but we're at the foci of the oval. And Mars is the same thing, except they overlap. And originally, they were on resonant orbits. The Earth on a 360-day orbit, Mars on a 720-day orbit. But there were times when they came near each other every 108 years. In the spring, if they came near each other in the spring, it would be March 20th, 21st. It would be inside after perihelion, and Mars would lose a little energy, Earth would gain a little energy. They'd pass again every 108 years, but the next one would be in the fall, October 25th, and it would be, this time it would pass behind the Earth, and there would be the Earth would lose a little energy, Mars would gain a little energy. This kept going on until it finally stabilized And that's when the 360-day orbit becomes 365 and a quarter. That's why we have a leap year and some months different. And that's at Mars, it went from 720 down to 687. Earth gained a little, Mars lost a little. Now, that's a theory, but it turns out there's a tremendous amount of support for that. But one of the most provocative confirmations comes from all places from the travels of Lemuel Gulliver, which is a children's story written by, as we would look at it, by Jonathan Swift. It actually was some political satire of the day. We regard it as some children's stories. But before we get into that, I want to review telescope technology. Most of you know that Galileo was famous for the first serious use of the telescope in 1610, and with that he discovered the 4 moons of Jupiter and Saturn's rings. Big deal. 1781, Herschel, with a better telescope, discovers the planet Uranus. A little later, a couple of years later, in fact, 6 years later, he discovers the 2 moons of Uranus. And then a couple of years later, he discovers 2 more moons. See, the telescope technology is improving, better telescopes. Till you get to 1846, Leverrier discovered Neptune and one of its moons. Then you get to 1877, a guy by the name of Asaph Hall, with a brand new telescope in the United States Naval Observatory, he makes astronomical history because he discovers that Mars has 2 moons. They didn't know that. And he names them Deimos and Phobos. And Deimos has an orbit about 30 hours and 18 minutes. See, our moon has a 30-day orbit, right? This one has a 30-hour, it's 18 minutes. And it's almost synchronous. In other words, it would appear almost to be stationary. And then Phobos is 7 hours and 39 minutes. And Phobos is unique in the entire solar system. It's the only one that goes backwards. Everything else goes westward. This one particular satellite, for some reason, is going eastward. And the reason it's so hard to see, it's very small. It's only 8 miles across. And it is almost black. It has a reflectivity of only 3%. In other words, it's almost black. That's why it's so hard to see. That's why it made such history when Asaph Hall spotted it. Little background. Well, that's 1877. Jonathan Swift published his story called Gulliver's Travels. It actually was a collection of essays for political satire, but in 1726. Now, we all know the Gulliver who visited the place called Laputa with all the little people, right? That's our story. The third voyage of Gulliver, different story, but in the same collection, is he goes to a place called Laputa. And in Laputa, the astronomers there are they make fun of London because they know about the 2 moons of Mars and the people in London don't know about it. It's just in the story, just a colorful children's story, except in the story, it details the size and the revolutions of these 2 moons of Mars within about 20% of what we know of them today, and it mentions that one of them is going backwards. Now, the problem is, how did Jonathan Swift put that in the story? Because he published that 151 years before the astronomical world discovered the 2 moons of Mars. Well, we don't know. We presume that what Jonathan Swift did was that he drew upon some legends to embroider his little story. He probably didn't realize that what the legends that he was drawing upon were actually eyewitness accounts. They'd have to be eyewitness accounts because this 151 years before you had the telescope technology to see these things, unless Mars got so close on one of these pass-bys that you could see them with the naked eye. That's why this is such a provocative piece of news. Now let's talk about the long day of Joshua. 1/3 men were at Beth Horon. And October 25th, 1404 BC, Mars was on a polar pass at 70,000 miles. That's very close. And appeared to rise 50 times the size of the moon. Severe earthquakes and land tides. Polar shift of about 5 degrees would lengthen the day, incidentally. Meteors followed about 2 or 3 hours later at about 30,000 miles an hour. And this whole drama is included in other ancient legends and folklore also. There's we're indebted to Emanuel Velikovsky, who discovered there's a legend of a long night in China in this period. So all this seems to be corroborative of what the Bible sounds so strange to us, but we discover when you get behind the scenes, it's not so strange. Well, let's get back to modern physics. Under Einstein, of course, we know that if we have a four-dimensional space-time, we consider it curved by the presence of matter, producing a universe whose geometry is Riemannian rather than Euclidean, and we covered all that in one of these previous things. I don't want to go through it all again, but I want to tie it to some of the things we've done before here. And the whole idea that bodies that travel in geodesics, that shortest paths, are curved orbits interpreted by Newton as a result of some attractive force. And then we have the scientists looking for gravity waves. We're spending a lot of money on GEO 600 looking for things called gravitons. And we covered that last time in the beyond perception thing in terms of looking for these particles. We've never seen them, but they assume they exist to account for gravity. And these are massless, uncharged particles moving at the speed of light, presumably, but so far they're undetected. These are fabrications of imagination to try to repair some theories. And the GEO 600 experiment, which they're looking for the gravitons, they've discovered, more interestingly, evidence that we may have a holographic universe. We've talked about that before, but I want to get this in perspective. So I want to get into this epistemology 101 issue. I want to talk about the scientific method. We use that phrase all the time. What we really mean is the empirical method. Well, how does it work? The concept of the scientific method is, number one, you observe a phenomenon. You see something and you measure it and take recordings. Then what you do is you seek patterns and measures of your observations. That's all gathering, data, in other words. Then you formulate a hypothesis, a conjecture, if you will, from that description. And then what you try to do is you gather independent data to challenge the hypothesis. That's what we mean by the scientific method. Now, it may shock you to realize that your whole process is to search for failures. You've got this hypothesis, you want to try to disprove it. If you can't disprove it, that reinforces the credibility of your hypothesis. Theories can never be proved. That may shock you. They never can be proved. What they can do is they might defy being disproved. Someone has a theory, great, you try to disprove it. If you can't, that starts to elevate that hypothesis to the level of a theory, but it may get more and more credible the more you try to disprove it, but it's never really proven. That's an important concept to get across. Now, Shannon, we're now in the area of what we call the information sciences. Claude Shannon defined what he called the verifiability definition of meaning. What do we mean by meaning? It has to be verifiable to have meaning. Untestable statements are meaningless. Grandma says there are gnomes in the garden, but they always manage to be invisible when you're looking for them, you see. Well, we smile at that, but the point is, you see, that's a meaningless statement. Why is it? Because there's no way to verify it, you see. Well, you can't disprove it. That's not proving it's true. So untestable statements are meaningless, according to the Shannon verifiability theory of meaning. Huxley said, the great tragedy of science is the slaying of a beautiful hypothesis by an ugly fact. You see, facts that aren't convenient for your theory, often people try to discard them. Well, find some excuse why that doesn't fit the theory. Well, that's not being scientific. Non-falsifiable hypotheses are not only non-scientific, they're intellectually dishonest. The idea of a hypothesis, it should be testable. And if you can test it and can't disprove it, that doesn't prove it's true, but it gives it a step in that direction. In logic, they have a thing called argumentum ignorantium, the argument from ignorance. The assertion that something must be true simply because it hasn't been proved false is nonsense. And yet we'll find ourselves, if you're not on your guard, we do that all the time. Because you can't disprove it, it must be true. No, no, no. Error, error, error. So if you can't use scientific method, and many people can't, people that are dealing with cosmology, what happened 100 billion years ago, we don't know. In other words, you make guesses, and remember that they're guesses, fine. What are substitutes for the scientific method? Well, one is called the deductive method. You derive theories from generalizations about the universe. Somebody has a generalization that seems acceptable, and we derive theories from that. That's not the same thing as proving they're true. You follow me? They're deductively logical, yeah. Here is the big one. what we call mathematical proofs. People make very elegant consistencies within a synthetic universe, a man-made. Mathematics is sometimes called the man-made universe. You define some symbols, and you define how they relate to each other, and you find that that relationship or that model is useful. And so you start getting into that more and more elegant models. The thing you lose sight of is you want to have evidence that that model fits reality. Many times it'll fit reality for a certain domain, but not others. And examples are, there are rules that occur in physics of the kitchen that don't fit in the area of the atom. The equations are different because there's different forces at work and so forth. The point is we can make very, very elegant models mathematically, but they are not reality, no matter how elegant they are. And one of the things we're discovering is that some of the most brilliant minds on the planet Earth are deeply involved in the most elegant mathematics you can imagine. That doesn't mean they fit reality. And that's what we're going to discover. Much of the theories about the so-called Big Bang, these things that come out of astronomy and astrophysics, are being end run by ugly data. Doesn't fit the model. There's another thing called domains of validity. I've touched on that. There's a model or a set of equations that may have a limited domain of validity, and that's why it needs to be tested. They have carbon-14 for dating, but it turns out for long dating, there's errors that creep in. So you always need to validate the model you're using. But the other thing that's taken place in the scientific world, in the absence of those things, are what we call peer review. In other words, you've got a scientific theory, you submit it to a publication, and you have other scientists that are considered your peers react to that and to give it encouragement or discouragement, if you will. It turns out that's the way our world really works. Publish or perish is the idea in universities. You need to publish that in a peer-reviewed journal and get their reactions. If they like it, you're elevated. If they don't, you're rejected. You're a victim of the peer review. Well, that just ossifies or freezes the current assumptions. And it really results in the censorship of competing hypotheses. If the people reviewing your paper hold theories that are different than yours, they're likely to disparage that. And that's not just in theology, it's even in physics. That may surprise you. So some caveats. Inference is not proof. You can make an inference, but that's not the same as proof. Something else, to give you another example, you want to avoid the logical fallacy of asserting the consequent. Let me give you an example. If A, then B. In other words, if B is true, therefore A is true. That makes sense, doesn't it? Not necessarily. The street is wet, therefore it must be raining. No, this ignores a possible alternative issue. A street cleaning machine just went by. See, just because if A then B, and you happen to know B is true, doesn't mean A is. Because we could give other examples, but that's the idea. The illusion of knowledge. The only one certain barrier to truth is the conviction that you already have it. And that pervades in most people in professional fields because they believe they've got a truth, and that makes them blind to competing truths, if you will. And Borson's saying, the greatest obstacle to discovery is not ignorance. It is the illusion of knowledge. The Lord has haunted me with this phrase for many, many months, and now I'm beginning to understand what He's leading me to. Metaphors reign where mysteries reside. How often there's something we don't understand, we give it an elegant name or an anecdotal relation, and that takes over instead of analyzing the mystery. Metaphors reign where mysteries reside. Science versus we say science and technology. Great. What's the difference between science and technology? Technology produces useful products. That's why we have cell phones. That's why we have computers. That's why you can make a long list of the incredible things that have come to us in the last 30, 40 years. The changes are astonishing from technology, because technology is validated by having things happen. Okay? Science has become a religion with a priesthood. I've used this before, but I love it. It just fits here. It's a little poem I saw as a kid. I find it fits physics so perfectly. The Blind Men and the Elephant. It was 6 men of Indostan, to learning much inclined, who went to see the elephant, though all of them were blind, that each by observation might satisfy his mind. The first approached the elephant, and happening to fall against his broad and sturdy side, at once began to bawl, "God bless me, but the elephant is nothing but a wall." The second, feeling of the tusk, cried, "Ho, what have we here? So very round and smooth and sharp, to me 'tis mighty clear, this wonder of an elephant is very like a spear." The third approached the animal, and happening to take the squirming trunk within his hands, thus boldly up and spake, "I see," quoth he, "the elephant is very like a snake." The fourth reached out his eager hand, and felt about the knee, "And what most this wondrous beast is like is mighty plain," quoth he. "'Tis clear enough the elephant is very like a tree." The fifth, who chanced to touch the ear, said, "Even the blindest man can tell that what this resembles most, deny the fact who can. This marvel of an elephant is very like a fan." The sixth no sooner had begun about the beast to grope, when seizing upon the swinging tail that fell within his scope, "I see," quoth he, "the elephant is very like a rope." And so these men of Indostan disputed loud and long, each in his own opinion exceeding stiff and strong, though each was partly in the right, and all were in the wrong. So often theologic wars, or I'll say physics wars, the disputants, I ween, rail on in utter ignorance of what each other mean, and prate about an elephant not one of them has seen. That fits in my mind. So I want to talk a little bit about the milestones of influence. Obviously, Johannes Kepler had a huge impact on our understanding of the solar system. He's the one that recognized that the planets were in elliptical orbits with the sun at one of the foci of an ellipse, that the sun's radius vector sweeps equal areas in equal times, and the planet's squares of periods are to each other as the cubes of their mean distances. These are mathematical models that turn out to fit the planets. And so he's very famous. That was his contribution, if you will. Well, he's succeeded by Sir Isaac Newton, mine's one of the greatest men in science ever lived. He laid the basis of celestial mechanics. He's accounted for incredible advances in optics, use of color, and so forth. He's accredited with inventing differential and integral calculus. Some people say Leibniz did. They'd added who actually did, but certainly they're incredible people. He was a serious Christian, by the way. He wrote biblical hermeneutics in over 1 million words on Daniel and Revelation and so forth. But what he's really known for, most of all, eclipses these in science. That is, he is responsible for the inverse square law of the theory of universal gravitation. And that's what we're focusing on, because his influence on science and life in general from his universal theory of gravity is profound. But I want you to notice something that's in the official title of that, the inverse square law. That's overlooked by most astronomers. I'll come to that. See, that's the equation of the universal gravitational constant. The gravitational force is a constant times the product of the masses, two objects, divided by the square of the distance between them. Okay? And the g is just a constant depending on what units you're measuring things in. And g, by the way, may be decreasing a little bit, and that's a whole other thing. But the point is really, what everybody overlooks, you have two masses, and you divide by the square of the distance between them. You put them twice as far, they have 1/4 the gravity. You put it 3 times, it's 1/9 the gravity. See, it's the inverse square law. Now, we'll come back to that later. Ben Franklin you don't normally think of him as a man of science, but he made a discovery on June of 1752. He flew his kite with a key attached. And the amazing thing was that he wasn't electrocuted, by the way, but he determined that the sky was inherently electrical in nature. His discovery, really, his realization. No one picked up on it, but it's in the record book, so to speak. Michael Faraday comes along, born about the time Franklin died, by the way, And he discovered what we think of as fields, electromagnetic fields. Albert Einstein kept a photograph of Faraday on his study wall alongside pictures of Sir Isaac Newton and James Clerk Maxwell. So these are the greats, if you will. We'll come to James Clerk Maxwell in a minute. Faraday was highly religious. He was a member of the Christian sect that demanded total faith and commitment. Biographers have noted that a strong sense of unity of God and nature pervaded in Faraday's life and work. I think it's interesting that some of these great minds were God-fearing people. They had different doctrinal perspectives, but they were God-fearing people. Okay, Faraday is followed by a guy by the name James Clerk Maxwell. And he codified all of what we know today of electrical science and engineering into self-consistent equations. And so his impact is not fully appreciated by many, even to this day, and I'll come to that, although he's the foundation for what we call electrical engineering. Electric currents and magnetic fields intrinsically co-occur. They're linked together. Electromagnetic energy propagates through space. He is ranked with Sir Isaac Newton and Albert Einstein for the fundamental nature of his contributions in quantum theory, electromagnetics and electrostatics, thermodynamics, and information theory and cybernetics. And that's the ultimate science, by the way, we'll discover, is information theory itself. Maxwell's equations, you'll hear that term all among engineers, 4 partial differential equations that relate the electric and magnetic fields to their sources, charge density, and current density. These equations can be combined to show that light is a magnetic wave, electromagnetic wave. The interactions of electrostatic and electromagnetic forces are very non-intuitive. I'll show you why a little later as we go here. The forces are orthogonal, that is, the forces are perpendicular to themselves, if you will. Okay? The forces are perpendicular to the fields involved. The resulting plasma, we're going to discover, takes on a unique aspect as a composite body, a very distinctive character. That'll be clear as we get into that here in a minute. Individually, these equations are known as the Gauss's law for magnetism, Faraday's law of induction, and Ampere's law of Maxwell's correction. These 4 equations, along with the Lorentz force law, complete the set of laws of classical electromagnetism. Fabulous though these are, what's astonishing we're going to discover is the astronomers have tended to ignore this to their detriment. Well, along comes a guy by the name of William Thomson, who gets knighted as Lord William Thomson, Lord Kelvin they call him, and he's one of the most influential scientists in 1900 Great Britain. Okay? He was knighted for his work in thermodynamics, but he was a very outspoken critic and pessimistic about the future of electricity and electromagnetic theory. He felt that radio and wireless telegraphy had no future. Now, he's a very, very influential man, but he took a position against electromagnetism, and as a result, the whole British scientific establishment tended to go down a path of ignoring Maxwell. Okay? He'll be rediscovered later, but the point is, he is thus, while he's very influential in very positive ways, he's negative in terms of his impact here. Okay? So I want to pause here and talk about a model not of our solar system, let's put it this, the solar system is the sun and all the 9 planets, okay? Let's make a model. There is a celestial publication, almanac, in which Burnham notices something interesting. The number of inches in a mile happened to be 63,360. Just happens, that's how many, in a mile, that's how many inches there are. In astronomy, the distance between the sun and the earth is considered a basic astronomical unit. They use that as a unit of measure. Well, it turns out a light year is how far light can travel in a year. That's another measure. The number of astronomical units in a light year happen to be roughly the same number of inches that there are in a statute mile. That suggests then an interesting scale to use. If you're going to build a model of the galaxy, why not use the inches, let an inch represent an astronomical unit, and build your model? You follow me? To get a feeling for these distances, okay? Well, the astronomical distance from the sun to the earth is an astronomical unit, as I've mentioned. Now, in Burnham's model, 1 inch represents the distance from the sun to the earth, right? Okay, so we start, and of course 1 mile represents a light year. So we start to build our model, we need to make a place to start, the sun. The sun's about 880,000 miles in diameter. It's about 90, if I'm going to take that part of 93 million miles that the sun is from the Earth, I've got to make the sun 0.009 of an inch. Now, make a dot with a very sharpened pencil, like a period. That's going to represent our sun. 1 inch away, we put the Earth. You with me so far? Okay? So let's call it 1/100th of an inch diameter is a tiny speck. And all the planets will turn out to be within a 7-foot circle. Mercury will be about 4/10 of an inch away from the sun. Venus about 7/10 of an inch. Earth 1 inch by definition, right? Mars about almost twice that, 1.6 inches. Jupiter about 5.2 inches. Saturn 9.5 inches. Uranus about 19.2 inches. Neptune 30 inches. And then Pluto 39.5, almost a meter, call it. Okay, so it turns out if we were building this model, we could put the whole thing inside of a 7-foot circle, right? You with me so far? Okay. Now we want to put the nearest star. Well, the nearest star is 4.5 light years away. Okay, so we have to put that star 4.5 miles away. Get the picture. The Earth and the sun is 1 inch. The next star is 4.5 miles away. Do you get a feeling for the sizes here? Okay. 2 specks of dust 4.5 miles apart. How much gravity would you think would have an impact there? The distance between them is squared and divided into it. In other words, it's de minimis. De minimis. If we visualized the sun as a golf ball, the next star would be 700 miles away. If I've got 2 golf balls separated by 700 miles, how much gravity do you think they feel with each other? None, of course not. So if we made this model further, our Milky Way galaxy would be 100,000 miles in diameter. Now let's back up a little bit and refresh some things we learned from some of the earlier sessions here. If we have a model of the atom, we went through this before, you got a nucleus and an electron. This is not to scale, obviously. We know nucleus is in the neighborhood of 10 to the minus 13 centimeters. The atom itself is about 10 to the minus 8. The ratio of that is about 10 to the 5th. If the nucleus was 1 inch, there's 100,000 inches in the orbit. 10 to the 5th. 100,000 difference, okay? But that's linearly. If I want to look how much area does that, we have to square that, right? It's square. If we're making a 3-dimensional model, well, first of all, a 2-dimensional model, we've got to square that, okay? And if you want to get the volume, you've got to cube it, right? Length, width, height, right? So you take 10 to the 5th and cube it, you've got 10 to the 15th. That's a big number. 10 to the 5th to the cube is 10 to the 15th. How much is that? That's a ratio, the same ratio that 1 second would have to 30 million years. So if I have an atom anywhere, and I say there's nothing there, and you insist there's something there, I'm more right than you are as 1 inch. I mean, the physics of it would be the physical part of it is same ratio as 1 second would be to 30 million years. In other words, this podium is mostly empty space. The part that's not empty space is the same part that as 1 second would be to 30 million years. Why does it feel solid? Because it's an electrical simulation. The electrons of the atoms that make up this podium are colliding with the electrons that make up the molecules in my hand. That makes it feel like it's solid because they are colliding in a predictable way. But is there really is there something solid there? No, it's mostly empty. Hard to get used to, but it's important to see where we're going. We touched all of this on beyond perception, and as these various nuclei share electrons, you start making atoms become molecules, and those molecules become other things. So, if we start with a lot of nuclei and a lot of electrons, that's called a plasma. And so I'm using oxygen here as a blue dot and hydrogen here as a yellow dot. If I have a whole bunch of oxygen atoms, and they capture electrons that are free electrons. When it's in the plasma state, they are flowing as pieces. But as they start to get associated with each other, they become a gas. And the gas, as you start cooling it down, from gas down, you finally get a liquid. It gets into, the liquid. And like propane, we have propane, you get liquid. And then finally you get down to a solid. Okay. If you heat the solid, it becomes a liquid. You heat the liquid, it becomes a gas. When you heat the gas, it can become a plasma. The big thing is don't confuse plasma with gases, okay? Because plasma has a whole different behavior. We've got a little model up here that you can take a look at where you can see the behavior of arc. Plasma has three modes. We're going to get into that in a minute, in the next session actually, where the plasma where you have it's dark. Other conditions it will be glowing, and then it's got a third mode called arc mode, where it actually is like lightning or like a welding torch and so forth, and or like what goes inside in a fluorescent light, similar kind of thing. The nature of matter. Now, as you go from you have four states of matter, not three. Most of it are solid, liquid, and gas. No, there's a fourth that we all overlook. Plasma is the most random, solid the most orderly, most structured. Everything else is measurably between those. It's interesting that while the British were disparaging electromagnetism, the people up in the Scandinavian countries, in Norway and Sweden, their scientists were fascinated with the auroras. And they quickly realized that the auroras are electrical. And so they really got into plasma physics. The founders of plasma physics, in large measure, were the very northern latitudes. And this happened to be a surprised one in the southern hemisphere that occurred just a few weeks ago when I was down in New Zealand. And it was observed from the International Space Station. That's clearly, it's a aurora australis. So we have a plasma universe. The effects of gravity are minuscule. They're not a factor. I'll show you how much in a little bit here. The effects of electromagnetism can be 10 to the 39 times as great. The entire volume of our galaxy is filled with diffuse clouds of magnetized plasma, electrically charged ionized particles. 99% of all matter in the universe is in the form of plasma. Scientists are busily looking for the missing matter. That missing matter is hypothecated to try to preserve their theories. It's not missing. It's there in the form of plasma that they don't recognize. Let's take a look at Andromeda, M31, one of the most famous things in the sky. Beautiful thing. When you look at it in infrared, you begin to realize there's electrical things going on in there. It's not just simple solids. There's significant differences there. M82, if you look at it in different wavelengths, you begin to realize it's an electrical phenomenon. And there it is in the infrared. And it goes on like this. We begin to realize that these celestial objects are much larger than they first appear, and they're connected electrically, not gravitationally. Gravity has nothing to do with it, or little to do with it. These things are electrical phenomena. The more you know about plasma, the more these things can be recreated in the laboratory in smaller size that follow the same laws. And some of these things are really bizarre. You can't explain them with gravity. Here's the star V838 from the Hubble telescope on May 20th of 2002, then September 2nd of 2002, October 28th, 2002, and December 17th, 2002. And it's hard to explain what's going on here by gravity, by the way. See, gravity only attracts, doesn't repel, and there's a lot of other things going on here. Let's talk about our closest neighbor, the sun. When we have an eclipse, we begin to realize there's a corona, and that starts to evidence that it's electrical in nature, not gravitational. And there's a common myth that that's a thermonuclear process going on. Not so. We're going to discover in the next session what it really is, and that may surprise you. Because we begin to see, if we look closely at the corona, we begin to see things that are happening that are not gravity at all. And this is a picture of the corona. We're going to talk more about the next session. But I got a movie I'm going to try to show you. As you watch these corona flares and so forth, it's obvious as you watch them they're following magnetic paths, electrical paths. they're behaving according to a set of laws which are understood, and from that behavior, we don't have all the answers to all the questions, obviously, but it's amazing how much of what we didn't understand about the sun suddenly does make sense. Well, this series is the fourth in a series called The Boundaries of Reality, and I'm using the Vitruvian man as a symbol of man's reach, as I have before, and the other things. Size is increasing to the right here, and in our early things we talked about the macrocosm, of course, which is finite. That gets us into astronomy and astrophysics and all that. We then went into the quantum physics, the microcosm, smallness, and as we explored that, we discovered the universe is made of indivisible units, basic units that can't be divided. That's the field of quantum physics and subatomic particles. And the metacosm that this is all in then, putting this all together, is we discovered is actually a digital simulation, because on the large side it's finite and quantified, and on the small it's quantified. It's always made of indivisible units. Now, in an article on this subject in the Scientific American, they point out that if these units are changing their size, then that implies that our reality is but a shadow of a larger reality. So far we've talked about the big side, the macrocosm, the microcosm. We now have gotten into we're going to get into next session zero-point energy, which will lead us into plasmas, and we have closed the loop, if you will, of this entire program. And so that's our next session. Okay, we're in part 2 of our exploration, what I call Beyond Newton, and we're going to discover what we mean by the plasma universe. It's interesting, there's a quote in Psalm 19 we'll be talking about, which speaks of the sun. His going forth is from the end of heaven and a circuit unto the ends of it. And that's exactly what we see happening in the sky. People say, well, the sun doesn't rise in the morning and set in the evening. The Bible's wrong. No, it's taking a global view because the sun is moving in a circle itself. Let's just review something we talked about earlier. I want to focus in on that, the kind of beliefs that we hear talked about in astronomy. There's a black hole in the center of that galaxy. Otherwise, we cannot explain the level of its energy output. Oh. Well, there's invisible dark matter in that galaxy. Otherwise, we cannot explain how it rotates the way it does. See, they have to postulate that to explain to confirm their theories. 96% of the universe is made up of dark energy and dark matter we cannot see. Really? You'd think that would make us at least suspicious. See, otherwise, the clusters of galaxies would fly apart because gravity alone can't hold them together. So it never occurred to them that it might not be gravity we're looking for. They just figure if gravity alone can't do it, there must be more gravity somewhere, more mass. Pulsars are made up of strange matter. Otherwise, we can't explain their oscillator-like behavior. Really. Photographs of connections between two objects that have different redshifts are only chance alignments. Really. And the examples are, there's a couple of galaxies that are clearly different redshifted, which means they're way apart, line of sight-wise, and yet they're connected. They can't explain that. Well, that's just an accidental co-occurrence, really. Otherwise, the Big Bang is falsified. Oh. As Halton Arp was Edwin Hubble's assistant and longtime observer at Mount Palomar and Mount Wilson telescopes, his photographs contradict the Big Bang theory in the first place. You think they would get suspicious. Well, that's what we're going to get into. There are myths in the midst here. The illusion of there's only one certain barrier to truth, the conviction you already have it. The greatest obstacle to discovery is not ignorance, it is the illusion of knowledge. Metaphors reign where mysteries reside. Science versus technology, we talked about in the previous session. And technology produces useful products. That's where the economy rewards that. Science has become a religion with a priesthood. The astronomers are really in a cul-de-sac of myopia or nearsightedness. Astronomers explain their views relying on 17th and 18th century tools of their forefathers, Kepler and Newton. Gravity, fluid mechanics, the magnetism of lodestone, rather than those of the 19th century, James Clerk Maxwell and the electromagnetic field theory. You see, they're a century lagging here. Furthermore, the astronomers are not actually empirically based. They choose to ignore data that isn't consistent with their conjectures. They must postulate particles not seen, gravitons being an example, and forces not yet experienced. Well, that's ignoring the absence of that information. Sir Isaac Newton, he wrote Principia back in 1687. It translated, it was in Latin, then in English, 1729. Gave the foundation of calculus, extended the understanding of color and light, mechanics of planet. But his big thing was the inverse square law of universal gravitation. That inverse square law. We talked about this last time. We're going to pick up on this now. That's the equation, okay? M1 times the product of the two masses divided by the square of the distance between them. That's the thing that you want to keep an eye on. Well, the astronomers like to talk about gravity waves. There's millions and millions of dollars being spent on equipment searching for the gravitons. Relativistic gravitational field theory implies the existence of particles called gravitons as carriers of the field. They're massless, uncharged particles moving at the speed of light, but so far undetected, so we've got to spend money to detect them. Try, okay? The GE 600 project in Germany is an example of that. What they have discovered, that we may be in a holographic universe, whole other study. We mentioned that in the previous series. The Burnham model, we took that last time, but to get it fresh in our minds now, we've got, we're going to use inches in a statute mile to represent astronomical units, okay? The distance of the sun to the earth is an astronomical unit. So 1 inch represents the distance from the sun to the earth. 1 mile represents a light year. And this is from the Celestial Handbook. That's a standard thing in astronomy, but adopting this to get a perspective is useful here. If you take the sun as 1/100th of an inch in diameter, so it's a speck the size of a period, all planets are then inside a 7-foot circle. Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, and then Pluto are all within going to diameters now, twice that. In other words, it's a meter in radius or 2 meters in diameter. Call it 7, 8 feet. Well, the nearest star is 4.5 light years away from us. So on our little model, we have to put a speck the size of a period 4.5 miles away. What do you suspect, according to Newton's law of gravity? You take the product of their masses, divide by the square of the distance between them. What have you got left? Nothing, really. 2 specks of dust 4.5 miles apart. If you can more comfortable visualize them as golf balls, they are 700 miles apart. How much gravity do you think 2 golf balls, 700 miles apart, feel towards each other? Okay, so see, what everybody overlooks is this d squared. The distance between them, you take it and you square it. That's a second order function here. Back in our discussion of fundamental forces in beyond perception, we talked about electromagnetic and weak forces. Gravity is 10 to the minus 38. Electromagnetic is 10 to the minus 2. What does that mean? That means the electromagnetic force is, that's oodles, 10 to the 30. Those are orders, it's not 10 times as big, it's 10 with 38 zeros after it, bigger. And not only is it incredibly more strong, it also, in both directions, it's positive and negative. It can repulse. it not only can attract, if they're unlike charges, they can push each other away. The electromagnetic force, whichever way it is 36 orders of magnitude beyond gravity. Okay? So it's what's ruling, not gravity. Gravity is, once you start dealing in these large distances, gravity evaporates us into irrelevancy. Electromagnetic is what it's really all about. And that's been ignored by the field of astronomy for some very interesting reasons. This aurora we mentioned before is just indicative of the kind of physics phenomena. When we go to some of these little toys, like the little display thing there, you put your finger on that, you can play, when you get a chance after the thing, you can go play with it, just put your hand on it, you'll see the filaments there, the plasma filaments follow you as what you're doing. And it's obviously not gravity that's doing that. We talked about the fathers. We went through the different guys, Faraday and Newton and so forth. Let's pick up the founders now of plasma. Christian Birkeland. He made a heroic commitment gathering data from aurora displays. He was the first to recognize that electric currents flow from the sun to excite plasmas in the Earth's upper atmosphere. We call those auroras. He studied them. The Brits chose to ignore them. The Swedes and the Norwegians studied them a lot and made all kinds of exciting discoveries. And Birkeland is a legend in this field. He discovered the twisted corkscrew-shaped high-intensity currents in plasmas that follow magnetic fields rather than cross them. These are called Birkeland currents. I'll show you some in a little bit here. He was nominated for the Nobel Prize in Physics 7 times. His portrait remains on the 200 kroner Norwegian currency to this day. You've got a 200 kroner note, you'll see his picture on it. He's a legend there, unheard of in the Western culture, or I should say the British culture. Well, he's followed by Erwin Langmuir. He discovered what's called the double sheath or double layer in plasmas, and I'll get to that in a minute. He coined the term plasma. He's the one that many people just called it ionized gases. He coined the term plasma because these are so they're not like they're different than a gas because they're electrified, and he used the word plasma to describe these almost lifelike, self-organizing behavior of these ionized clouds in the presence of electric currents, magnetic fields, foreign bodies that are inserted to them. You put a foreign body in them, and it surrounds them and double sheaths it, and that's what he discovered, and it's named after him. He invented the Langmuir probe, still used today. Now let me explain what these double layers are. One of the most important properties of a plasma is its tendency to isolate one section from another electrically by a wall of two closely spaced layers, one of positive charges, the other of negative charges. And a DL, as it's called, or double layer, is where the strongest electric field in any plasma will be found. The plasmas will isolate themselves from foreign intruders by surrounding themselves with a double layer as a protective sheath. So you plunge a sphere in there, and the plasma will enclose it, if you will, with a double sheath. And that has some very unusual behavior I'll come to in a minute. Well, after Langmuir, then Langmuir, he invented a probe that was a way of measuring what's going on inside the double layer. That's called a Langmuir probe to this very day. It's a clever device that he invented. But here's the big guy. This is the guy who's just a legend. He just died in 1995. Hans Alfvén. And he was the first to predict the large-scale filamentary structure of the universe back in 63. Now, there's two things about that. They've known about this some time, on the one hand, over 40, 50 years, 60 years. But it's also interesting, these fathers of science are recent. They're our generation, so to speak. Maybe not yours, but my wife and I, anyhow, okay? So science has gotten contemporary with plasmas. He first proposed the mechanism for the acceleration of cosmic rays, now known as the Fermi mechanism. He was awarded the Nobel Prize in Physics in 1970 for his work in magnetohydrodynamics, a closely related field. In February of 1981, 11 years after the Swedish electrical engineer Hans Alfvén won the Nobel Prize in Physics, he published Cosmic Plasma, a book which has been largely ignored by the astrophysics community. That's what's so amazing about this. People aren't open to new ideas. this was seen as a threat, then they dismissed it rather than embraced it, or even just evaluated it. Yet our space probes have since confirmed his views. Over 99% of the universe is composed of electric plasmas, and they obey the same physical laws as small laboratory plasmas do here on Earth. Okay, now that little thing down there, the little toy we showed you, is just a toy, really. Don't confuse that with a laboratory thing, which is far more elaborate, but nevertheless. Then we have Anthony Perrott, author of a book called The Physics of the Plasma Universe, Numerical and Experimental Contributions to High Energy Density Plasmas and Intense Particle Beams, Explosively Driven Pulse Power Generators, that sounds like weapons to you, lasers, intense power microwave sources, particles, high energy density phenomena, Z-pinches, I'll come back to that, and inertially driven fusion target designs. At Los Alamos National Laboratory from 1981 to the present, serving the Applied Theoretical Physics Division, Associate Laboratory Director for Experimental Programs, and a scientific advisor to the United States Department of Energy, where he served as acting director for national security and so on and so forth. His large-scale simulations of the Maxwell-Lorentz equations yield results virtually indistinguishable from astro images of actual galaxies. You want to see a few? There they are. These are simulations he's done in the laboratory demonstrating the same behavior, and I won't go through all the step-by-step what's going on here because it gets into some other issues too. But basically the main point of this is his simulations in the laboratory fit the behavior that we observe in the heavens, millions of light years away and all that. Well, back to the atom that we talked about before, as you know, we went through this, that if you take the volumetric ratio of what's going on in the atom, you've got a ratio of physical things to space, the same ratio as 1 second has to 30 million years. It's mostly empty space, but what it is, it's electrical charges. It's electrical field. That's what's really the relevant thing that's going on here. And we talked about how molecules, we did this just by way of review from last time. We'll keep moving here. If you cool the plasma, well, first of all, you have these molecules that start attracting electrons. When they pair up, they cool down, they pair up, they become a gas. But that's a different thing. The gas cools down, it becomes a liquid. And as the liquid cools down, it solidifies what we call a solid. And if this happens to be a H2O, then it's ice, and it shows up in the crystalline form as one example of that structure. Now, these four states of matter, solid, liquid, gas, plasma, are plasma is the most disordered, random aspect. As you cool it down, it gets more orderly. Solid is very, very orderly. If you heat it so it's fluid, it gets a little disorderly, it's called liquid. It doesn't have a shape. And then you get the gas where it'll just expand to whatever volume is available. And then you have the plasma, which is a creature of its own kind. And that's what most of the universe is, plasma. And so the effects of gravity on a plasma are minuscule. They're eclipsed by the electromagnetic forces on them, which we tend to the 39 orders of magnitude difference. And so the entire volume of our entire galaxy is filled with diffuse clouds of magnetized plasma that is electrically charged ionized particles. 99% of all plasma, of matter in the universe is plasma. And last time we looked at Andromeda, when you look at that in infrared, you begin to see the electrical behavior that's actually accounting for what's going on there. And M82, again, if you look at it, it depends what frequencies you're looking at, that'll determine what you see. Here you begin to recognize that you've got electrical factors going on enormous distances away from these that are affected by that. They're behaving together. It's interesting to me that in Job, God gives Job a science quiz in chapter 38, a very interesting chapter, but one of the things he challenges Job about, canst thou bind the sweet influences of the Pleiades or loose the bands of Orion? Well, you can quickly do some calculations and you discover the stars that make up those constellations are so far apart that gravity isn't binding them together. And God is challenging Job. Who do you think you are? Can you explain what ties that together? No, he knew nothing about plasmas. Okay? In Genesis 1, we have the firmament, the waters above the firmament, the waters below. Waters is the Hebrew term mayim. Does it mean really waters, or could it include plasmas? And that's something I'll let you sort out for yourself. Here's another galaxy where you can clearly see the electrical effects, and we'll understand that better as I get into plasma. James Clerk Maxwell, ranked with Sir Isaac Newton and Einstein for their contributions in quantum theory, electromagnetics and electrostatics, thermodynamics, information theory, that's going to turn out to be the key one, and cybernetics. Now, the Maxwell equations are these 4 equations. They're differential equations. I spare you the math, just to give you a flavor, though, that they relate the electric and magnetic fields to their sources, their charge density, and their current density. And these equations can be combined to show that light itself is simply an electromagnetic wave. Photons of light or photons of an RF signal, they're photons. The interactions of the electrostatic and electromagnetic forces are non-intuitive. In other words, they behave in ways you wouldn't suspect unless you've played with them a little bit, okay? The forces are orthogonal to the fields. You have a field, the force that field has is 90 degrees in a different direction. We think of a force, if I'm pushing on this, you're expecting it to yield the way I'm pushing. No, if it's a magnetic field, the force is 90 degrees to that. The resulting plasma of these things then take on a unique aspect as a composite body with a very distinctive character of its own. And that's what throws us. The individually equations are known as the Gauss's law for magnetism, Faraday's laws of induction, and Ampere's law with Maxwell's correction. And there's another law, the Lorentz force law, that with this package you have to master if you're going to be in electrical engineering, and they do. But applying it to this is then more easy to do because you'll have some intuitive feeling for how those laws work. The Maxwell-Lorentz law, and there it is for those of you that are curious about it, simply says the acceleration, what they mean by that, the time rate of change of momentum, experienced by a particle moving with a velocity v in a magnetic field B that is carrying, is simply the sum and then the product of that. It's very straightforward. No d squared divisor here. It gets strong. As these get stronger, it gets stronger, right? The force experienced by the particle will be at right angles to the direction of its velocity. In other words, the magnetic field is in one direction, the velocity of the particle is in another direction, the magnetic force on the proton is yet. These are all orthogonal to each other, which makes it hard to visualize until you've played with it a bit, okay? What engineers quickly learn is what they call the right-hand rule. And you have if you take your right hand and put your thumb in the direction of the current, your fingers are pointing in the direction of the field around it. If you have a field that's changing, then you'll have a current. If it's increasing, the current will go this way. If it's decreasing, it'll go the other way. But the point is, the right-hand rule allows you to connect the field around that wire. If you have current going through, it'll create a magnetic field. If you have just a wire and you have a magnetic field and it's static, nothing happens. But the field gets bigger, either stronger or weaker, current will occur. If it's getting stronger, current will go that way. If it's, you get the idea. Okay. So plasma turns out to have 3 different modes. There's a dark current mode. You don't see it because it's invisible. There are plasmodes around us probably that we can't see because they're very low intensity. The Earth's ionosphere, except during auroras, that's when they become visible. The ionosphere is what allows us to send radio waves around the world. If you send a radio wave, it goes out into space. But if you hit the ionosphere and it bends it, it's a form of plasma. It's invisible. You don't see the ionosphere. But if you're a radio ham, you know when they're there. It's old news, okay. The electric current in a dark current mode is very, very low current. If you get more current, then it starts to emit light, okay? And that occurs in auroras. That occurs in emission nebula, in the sun's corona, in comet trails. Those are plasmas that have enough energy that they're glowing. You have a fluorescent light. You've got plasma operations going in. That's why it's cold. It doesn't get warm. But it's because it's the plasma effect that's giving you the illumination. The brightness depends on the brightness, the intensity of the current, and the density of the plasma. All those will affect, and depending on what kind of atoms it will be, what color it is, and so on. Neon lights are an example. The color depends on what gas is being ionized. Well, then there's the third mode, that's the arc mode, and that's what we think of as lightning, for an example. Extreme brilliance and wide spectrum. Electric welding. So when you see someone with electric welding, you never look at it with your eyes. You can ruin your eyes doing it. That's why they wear special glasses. But an arc welding is a danger to spectators. You should understand that. The sun's photosphere. You never look at the sun directly. Lightning and sparks are another example of that. And now they're characterized by twisting filaments and also a lot of ultraviolet and radio frequency as well as what you can see. Now what they discover, they discover is a thing called the Z-pinch effect. High intensity electric current passing through a plasma will take on a corkscrew or spiral shape that was discovered by Birkeland. And he's famous. They call those now Birkeland currents. The most often occur in pairs. They tend to compress between them any material, ionized or not, in the plasma. And that being pinched in there is called the Z-pinch, just a name for it. And cosmic matter that you see out there tends to form an abundance of filamentary, stringy structures. And the initial velocity, if a particle is perpendicular to the magnetic field, the path the particle takes is a circle in the plane perpendicular to that field. Great. However, if the velocity of the particle is at a slight angle different than 90 degrees to the magnetic field, perhaps slightly in the same direction of the field, the path will then be a helix or a spiral. If it's exactly perpendicular, it makes a circle. If it's slight angle, it makes a spiral. It's logical, okay? The stronger the field is, the smaller the radius of the circle will be. No matter what the initial direction of the current stream, it will end up following the direction, of course, of the magnetic field. And here's what it looks like. In other words, if you got, they come in pairs, and they'll twist themselves into what you and I would call a helix. That's showing on the left side of that diagram. If you have a bottom view, you see not only are they weaving together, they're tightening themselves together, and what gets caught between them is anything caught there, whether it's plasma or not, gets squeezed. It gets squeezed hard enough to become a material. It may be ionized, but then it becomes it moves to the solid state. And that's the way you can start to create planets electrically, okay, as an example, or parts of it. The Birkeland current, born in both in the laboratory and in the cosmos, a pair of such spiraling currents will be observed. The interlinked pair will at first be magnetically drawn together, but after a certain proximity is achieved, a force of repulsion is generated that holds them apart. This configuration turns out to be extremely stable, interestingly enough. The resulting tightly wound pair is called a Birkeland current. That's a term used for these pairs, these filamentary pairs. The attractive and repulsive forces acting on this pair of currents creates a twisted, constricting cylindrical volume inside the spiral where extreme compression of matter can take place. When this occurs in cosmic space, the associated plasma filaments can be observed by the radiation they emit. It isn't necessarily in the visible range, but it's measurable. We also have a thing called the Markland convection, when several different chemical elements are contained within such a region of compression. They don't mix homogeneously. They tend to distribute themselves radially according to their ionization potentials. They have an electrical ionization potential, and that will determine how they rank order themselves. 24 million electronvolts, it's helium. 13, it's hydrogen, oxygen, and nitrogen. 11, it's carbon and sulfide. And then you got the metals, ferrous and silicon and magnesium and so forth. This is called the Markland convection. We think of convection in terms of heat and our heaters rising. So this is a different thing in plasma physics. It has to do with their ionization potentials. Well, let's talk a little bit about the fabric of space, because that's what we're really into here. What's really going on in space? Stretching the heavens. Is that just a metaphor out of the Bible? He alone stretches out the heavens in Job 9. Stretching out the heaven like a tent curtain in Psalm 104. He stretches out the heavens like a curtain and spreads them out like a tent to dwell in, Isaiah 40, verse 22. He stretches out the heavens, Jeremiah 10. Is this just an idiom all through the Bible? Yes, it is an idiom all through the Bible. Nothing in the Bible is accidental. It's all there deliberately. The Lord who stretches out the heavens. We could go on and on with these. All through the Scripture, we see the heavens stretched. In fact, we discover that space is not what most people assume. It's not an empty vacuum. We discover in the Bible it can be torn in Isaiah 64. It can be worn out like a garment, according to Psalm 102. It can be shaken in Hebrews 12 and Haggai 2 and Isaiah 13. It can be burnt up, Peter warns us in his second letter. It can split apart like a scroll, Revelation describes. It can be rolled up like a mantle in Hebrews 1 or like a scroll in Isaiah 34. Are these just figures of speech? I don't believe so. I think they're glimpses. This is metaphors reign where mysteries reside. Many of these things might be mentioned by a rabbi as a remez, a hint of something deeper. Let's talk about this idea of rolled up in a scroll. In order for something to be rolled up, there has to be a dimension in which space must be thin. And in order to be rolled up, it must be thin in some sense, and yet it must be able to be bent or rolled. So the very fact it can be rolled up implies there's an additional, whatever space dimensions it has, there's an additional one for this to take place in. If you visualize space as 2 dimensions, you can see it rolled up. But we know that space is 4 dimensions. Okay, then it's to be rolled up, it must be 5. There's got to be a space in which, a dimension that space that can be accomplished. So there is a direction in which it can be bent toward. Thus, there are additional spatial dimensions, and 10 is a current estimate by some. That's an estimate by modern particle physicists. It was also the conclusion of a Hebrew sage that wrote in the 13th century from his study of the Hebrew text of Genesis 1. Well, beginning back to space as we know it, there's a thing called the red shift. Back in the 20s, a guy by the name of Edwin Hubble suggested that the reason some stars are shifted to the red, and I'll come back to that in a minute, he called that the Doppler effect as an explanation. And that is still to this day the belief of most astronomers that the reason stars are shifted to the red is because they're racing away from us. It's like a Doppler effect of a siren. When a siren comes at you, it raises in pitch. When it goes away, it lowers in pitch. They say that it's sort of like that. Well, maybe not. In 1976, William Tift of the Stewart Observatory in Arizona noticed, for over 20 years actually, he documented what he calls aberrant and the digitized nature of the red shifts. You know, the red shifts, some of them aren't shifted to the red, they're shifted to the blue. So they're coming at us, not going away, if that's your explanation. Also, it's digital. It's like a piano. There's certain keys you can hit. You can't get between them. I'm not talking about the black notes. All the keys. They're digital, really. The piano's a digital instrument. When you hit a key, you get a specific frequency. And you get the next one, you get a different specific frequency. You can't get, not like a violin where you get between those. Okay. And so, in the 1980s, Guthrie and Napier at the Edinburgh Observatory spent 10 years challenging his view and confirmed that Tift was correct, that they can't be the Doppler effect. There's something else going on. And we get into the Rydberg formula. The Rydberg formula was invented by a Swedish physicist, Johannes Rydberg, and presented on November 5th of 1988. It was used in atomic physics to describe the wavelengths of spectral lines of many chemical elements. Every chemical element has a certain barcode, actually. I'll show you one. The barcode of the atom. This happens to be hydrogen. It's on a logarithmic scale, by the way. Every unit is 10 times the previous. You know, you go 10 meters, 1,000 meters. You have to understand what a logarithmic scale. Anyway, there are certain lines. If you use those lines, that characterizes hydrogen. Now we discover that sometimes it shows up shifted just a smidgen to the red. And they always assume, well, that's because that atom is moving away from us. Maybe, maybe not. Maybe something else is going on here. These spectral lines are due to the electrons moving between energy levels inside the atom, according to Barry Setterfield and others. Robert S. Millikan in 1925 noticed that the wavelengths of spectral lines were shifted from their theoretical positions and was among the first to recognize the energy in space was battering the atoms and affecting their movement. This energy came to be called the zero-point energy. Now this gets to another issue. If you take a cubic meter of space and you take all the matter out of it, there's nothing there. You got a vacuum. Not quite. It still has a temperature. So you cool it. You got it totally empty, and you cool it down to what's called absolute zero. you discover the shocking discovery is there's still energy in it. And they call that the 0-point energy. And the amount of energy that's in that is gigantic. And that's where any atoms in that space get its energy to keep on its orbit without spinning out or falling in. You ever wonder about that? You know, it's spinning around. It's attracted. It's negative. It's positive. It should be attracted, trying to fall in. But it's got energy that's keeping it separated because of the 0-point energy. Max Planck in 1911, and then Einstein, Stern, and all recognized that this pervasive energy was a universal phenomena and intrinsic to space itself. There's probably, I wouldn't be surprised if you'll find probably less than 1 in 100 astronomers that know anything about the 0-point energy. There's a lot of people, unless you're into physics in this way, you probably wouldn't know anything about it. Through the work of Heisenberg and others, it began to be understood that Planck's constant was actually the measurement of the uncertainty in the position of atomic particles. All atomic particles are being battered by that energy, and therefore their actual position is ambiguous. It's a statistical issue, in effect. In 1962, it was realized that this uncertainty of position was caused by the battering of this 0-point energy. People talk about the Heisenberg uncertainty principle, and most people talking about it don't know what they're talking about. What they describe is correct, but it isn't the cause. New Agers pick up on this and apply it philosophically. No. It's a specific physics phenomenon. The energy is independent of temperature or mass, and that's a shock to many people. In 1987, Al Puthoff showed that the electrons stayed in their orbits and did not go either spinning out or spinning in due to expended energy, precisely because of the energy they received from the 0-point energy. Using 25 different methods, 475 measurements on 11 different related quantities confirmed the following. By the way, you all know about E equals mc squared. E is for energy. This is the Planck constant. E is equal to the Planck's constant times the speed of light. What they've discovered is the speed of light slowing down, the Planck's constant increases. The mass of all the atoms increase. But always such that the product, the energy, stays the same. That's a recent discovery. Planck's constant, h, is increasing, and the velocity of light is decreasing. The energy, of course, stays constant. There's no energy made or lost. It's the fixed. But what we discover, as the speed of light's been slowing down, the mass of the atoms are increasing, among other things. So we discover that space has properties. The 0-point energy is about 10 with 95 zeros after it, ergs per cubic centimeter. It has permittivity. It has permeability. These are engineering terms, but there's a dielectric constant, there's a magnetic constant. These are all out of Maxwell. It has an intrinsic impedance. Any amateur radio knows that you have to tune your antenna to the impedance of space. It has properties of its own, not because of the atoms that are in it. The space itself has properties. It can be stretched, like the Bible says. The velocity of light at creation was over 10 to the 10th power faster than it is today. Currently, it's at the speed of gravity, and all that is changing, strangely enough. Well, let's get to epistemology. We talked about epistemology a little bit. Let's go to epistemology part 2, if you will. The final frontier of all sciences we now discover. You study advanced science, you'll quickly discover whatever field you're in, you're going to get confronted with what's called the information sciences. The boundaries of our reality are information. Quantum physics, the Heisenberg, Schroeder's cat, and all that business has to do with information theory. Microbiology. You're going to go into the microbiology, you're going to quickly discover your world is full of coding theory, switching theory. The DNA is a 3 out of 4 error-correcting code. And they can't explain the origin of life because they can't explain the origin of information, which is the antithesis of randomness or the absence of information. And the whole idea of the intelligent design debate is insanity, because by definition, randomness is the absence of design. You can't attribute design to randomness. You're stepping on your own foot. Randomness is the absence of design, and when you find elegant design, it can't be attributed to accident or randomness. So it's another refutation of evolution. In the astrophysics, we have now the fabric of space. It turns out to be an information issue. We now are discovering, or beginning to suspect, maybe more accurate, that our universe is holographic. It's like a giant hologram. It's a giant illusion. That's what David Bohm, a confrere of Einstein, wrote about because he was with Einstein. They were good buddies, but Bohm came out of the plasma world. He was known for his work in plasmas. And And he's the one that has first formulated that, and now it's starting to gain credibility because of the discoveries they've made at the GEO 600. And so we're now talking a lot, what we've been talking about is the plasma universe. And it's interesting to me, as my personal field has been in obviously a very modest way, the field of information sciences. And because of that, I've always been attracted to Psalm 19, which we'll just take a few verses of it. Psalm of David. The heavens declare the glory of God, and the firmament showeth his handiwork. Day to day uttereth speech, and night unto night showeth knowledge. There is no speech nor language where their voice is not heard. Their line has gone out through all the earth, and their words to the end of the world. Wow. Notice something. The heavens declare, the firmament showeth it. Day to day uttereth speech. Night showeth knowledge. There is no speech nor language where their voice is not heard. Their line has gone out through all the earth. Their words, you realize that every phrase in here is one of information. One of the titles of the Messiah is the Logos, the Word. There's an intimacy between the declaration of light, the first quote in the Bible, let light be, is all tied together. The line has gone throughout all the earth, and their words to the end of the world. That's obviously larger than the earth. What's larger than the earth? The solar system, at least, probably a galaxy, you name it. In him he hath set a tabernacle for the sun. The sun has a role, a place, which is as a bridegroom coming out of his chamber, and rejoiceth as a strong man to run a race. The sun is running a race? Yes, because we're going to discover the sun is not a thermonuclear bomb going off somehow. It is a light bulb, a very unusual one that's drawing energy from the plasma and converting it to energy we can use on the earth. His going forth is from the end of heaven, and his circuit, the sun has a circuit. Sure, the Bible says so. From the end of heaven and a circuit to the ends of it. And nothing is hid from the heat thereof. Really? That's interesting. Sounds like thermodynamics to me. And we can go into all this and the locations, but we'll discover when you study the location of the sun, it happens to be in a place and with a dimension that makes discovery possible. If it was closer to the center or further from what, you would not be able to see the star. There'd be all kinds of problems. And if you look at the sun in a total eclipse, we discover the corona, and we also discovered the spectroscopy upon which all of astronomy is based. But wait a minute. Why do we have eclipses of the sun? You probably have no capacity to imagine how precise that had to be engineered to have that happen. Let me show it to you. It was designed to be discovered. You have the sun, you have the moon, and you have us on the earth watching this, okay? It turns out, in order to have the moon exactly obliterate the sun alone and let the corona show around it, it has to have a relationship in both size and distance that's precisely right to do that. If it was a little larger, it would totally blot out everything. You wouldn't see anything. If it was a little smaller, what was left would blind you. It happens to be just the right size that it acts like a silhouette of the moon so that you can see the corona. And discovering the corona, you put a prism, you discover, ooh, there's spectra. And from the spectra, you discover you can tell what the chemistry is, and on it goes. So the distance between the eye and the moon and the distance to the sun and the radius of the moon and the radius of the sun have to have a relationship, precisely that. And the reason I put D1 plus D2, because I couldn't make the diagram clear to have D2 start with your eye. So the distance from you to the sun is D1 plus D2. That's just an artifact of my diagram here. But the ratio, in other words, the ratio of the distance to the moon to the distance of the sun and the radius of the moon has to be exactly that, precisely that, in order for us to discover the corona. Was that just an accident? I don't think so. If you haven't seen the video, The Privileged Planet, or the book by Legalis and this guy called The Privileged Planet, you really want to see that. It may surprise you to know the temperature profile of the sun is not what you suspect. You have the photosphere, that's the part you can see, the chromosphere, which is the part that surrounds that, and then the corona. If you look at the temperature profile, I got temperature on the left, and it's logarithmic, and it's in degrees Kelvin. And to the horizontally is the height above the photosphere. The temperature is higher in the corona than it is in the chromosphere or the photosphere. You wouldn't think so, would you? You think it's hot and it would cool as it goes out. No, 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 no. It turns out it's hotter in the corona as it goes out. Why? Because it's electrical. So you don't get away from this gravity mentality. Let's talk about the voltage profile of the sun. I got voltage vertically here, again against altitude, and we discover that it is pretty steady relatively until it gets to the chromosphere. Then the voltage drops like mad. Visualize that like a cliff that's going off. It's going to accelerate in speed. Okay? And on it goes. And if you're an electrical engineer, you recognize that it's almost identical to the profile of a transistor, a PNP transistor. It's not only as electrical, it's very recognizably operational as electrical phenomenon. Let's take a look at the currents in the sun itself, okay? We have, interestingly enough, we have the current entering the sun in what we would call the north and south poles, both entering there and exiting at the equator. Wow, that's not what you'd expect, would you? Huh? And when it does, this is showing you when the main current going through the sun as long as it's increasing in strength, it creates secondary currents that go the other direction with analogous to double layer. But the point is, if it's going in that direction, but if it's going in that direction less fast, so to speak, less intense, those go the other way. Okay? If the main magnetic field starts to weaken in intensity, the secondary surface current will reverse in direction, and the magnetic polarity of the loops will also reverse. These loops are going to respond to where that main current is increasing. It's the rate of change of that current that's creating the fields that are causing the behavior here. It does not depend upon the direction of the primary current. It depends on, is it increasing or decreasing in strength? Okay? These reversals occur every 11 years. So that's why we have sunspot cycles that are on an 11-year cycle, it turns out. Okay? Here is a picture of the corona, and you can see the plasma sliding along the magnetic field line, and it's a cross-section, if you will, of the corona. And by the way, the size of the Earth on here, the space between these things, the Earth is a speck. Not a speck, it's more than that. Maybe call it, on this diagram here, it'd be about the size of a dime maybe, where this thing here is about 2 feet in diameter. Give you a rough feeling for it. Now, you have the photosphere, and you have a strong looping current will produce a secondary magnetic field that will surround and try to expand the loop. If the current becomes too strong, then the double layer that contains it will be punctured. And the voltage current gradient becomes strong enough, the discharge path will break. The energy stored in the primary magnetic field will be explosively released into space. Piercing the double layer produces what we call a solar flare. See, all this is explained electrically. And here's a picture of it. And here's where I'd love to try to see if I can't show the movie. It's quite dramatic. Just as you watch this movie go, but it actually shows these things following their paths. It's as you watch these corona flares and so forth, it's obvious as you watch them they're following magnetic paths, electrical paths. They're behaving according to a set of laws which are understood, and from that behavior we don't have all the answers to all the questions, obviously, but it's amazing how much of what we didn't understand about the sun suddenly does make sense because it's a plasma. And the sun is, in effect, a very sophisticated transformer to transform the energy it can draw from the fields it's passing through into a form of radiation that can be helpful to the planet Earth. Back to Psalm 19:6, which you started with. His going forth is from the end of heaven, and is circuit unto the ends of it, and there is nothing hid from the heat thereof. The sun is the source of energy for the entire solar system. And all the planets, not just the Earth, get their energy from the sun. Now, every fall, we see the leaves fall. What we may not realize is these brilliant autumn colors are due to the presence of accessory leaf pigments that normally assist the plant in the photosynthesis by capturing specific wavelengths from the sun. These pigments become visible as the leaf dies in the fall. But we need to understand that these leaves have been designed skillfully, and obviously we won't go into all that details here, except to understand they were designed to convert that energy into oxygen and sugar. C6H12O6 is a form of carbohydrates, a sugar. And that is essentially needed by the animals. The animals create the CO2 that the plants desperately need to take, when it takes that energy to create those products. So the plants make not only the O2 that we breathe, it makes the sugars we eat, or the sugars the animals eat when we eat the animals, whatever. But that closes, you understand, the whole thing's been skillfully designed and balanced. So it's not just the universe that's been designed, the whole system we find ourselves in is incredibly skillfully designed. And I love it when people say, gee, the ozone layer, if it changes 1/10 of 1%, it brings cosmic doom. Really? Then who balanced it in the first place and who maintains its balance today? The more delicate that issue is, the more it proves it was designed not randomly. It's not a result of randomness. Photosynthesis itself means to build with light. Sugar factories are producing millions of new glucose molecules every second. Most plants produce more glucose than they use and store it as starch and other carbohydrates in roots, stems, and leaves. Each year, photosynthesizing organisms produce about 170 billion metric tons of extra carbohydrates. That's about 30 metric tons for every person on the earth. Well, much more happened in the Bible than we really have an idea. Following the fall of man, creation has been subjected to futility and bondage. We learn not only from Genesis 3, but from Romans 8. To reveal himself more clearly, the Creator has given us his word. His word is pure, we understand from a number of places. God puts his word even above his name. That's astonishing when you realize how jealous he is about his name. He puts his word even above his name. And that continues Psalm 19 then. The law of the Lord is perfect, converting the soul. The testimony of the Lord is sure, making wise the simple. The statutes of the Lord are right, rejoicing the heart. The commandment of the Lord is pure, enlightening the eyes. The fear of the Lord is clean, enduring forever. The judgments of the Lord are true and righteous altogether, and it goes on. No, as we understand our universe, we begin to realize it's a plasma. And God said, let there be a firmament in the midst of the waters. Let it divide the waters from the waters. And God made the firmament which divided the waters which were under the firmament from the waters which were above the firmament, and it was so. What do we mean by waters? Mayim in the Hebrew. They translated waters. Is it possible that might be referring to plasmas? And is the figment the boundary between them? Well, we have our little boundaries of reality design here. The Vitruvian man being representing the reach of man, size increasing to the right. We went through the macrocosm, the bigness, and we discovered it's finite, and that's studied by the field of astronomy and astrophysics. When we explored smallness, the microcosm, we discovered it's made up of indivisible units called quanta, so we call it quantum physics or subatomic particles. The metacosm that all wraps around this thing, we discover, is a digital simulation. It has finite limits. That is staggering in its implications. That means the real reality is something larger. We use the term spiritual universe, physical. Those are words that don't have, they don't rattle when you shake them for most of us. They're concepts that are a little ephemeral for most of us. But even the Scientific American articles that deal with the constancy of the apparent non-constancy of our constants. If the constants are changing, and we now know they are, our universe is but a shadow of some larger reality. And that's astonishing. And what's interesting, we've taken the excursion from the macrocosm down through the microcosm with beyond perception, and now this one, in which we introduce the concept of zero-point energy, which ties us back to The real macrocosm isn't the field of astronomy, it's the field of plasma physics. And that's a recent discovery, a recent awareness, and not surprisingly, our popular common literature and the background of most of the editors and journalists are way behind what's really going on. But the more you understand the frontiers of science, the more comfortable Genesis chapter 1 reads. And I encourage you to do two things: to get a flavor of what we think we know about the universe, but then get a commentary on Genesis that reflects all that, and discover that this collection of 66 books that written by over 40 guys over almost 2,000 years is a package that's been designed in detail deliberately, and that design had to occur from outside the dimensionality of time. It's a message from our Creator to let us know who He is, what He expects of us, and praise God, what we can do to please Him. Through faith we understand that the worlds were framed by the Word of God, so that things which are seen were not made of things which do appear. God bless you.